What's going on, guys? Nick here. In this video, I want to do a full transformers implementation in Python and TensorFlow. I've seen tons of tutorials showing you how to do this on video with PyTorch, but I've yet to see a substantial one that I think walks people through the start all the way to the finish of creating your own like mini GPT style model. So that's what we're going to do in this video. It's going to be split into several different sections. I don't even really know which video is going to be in which section yet because I'm kind of just doing this freeform, but in order to get this done, we're going to be using a collab that I am going to title GPT Practice. And this is going to be our own implementation of a GPT, as I mentioned earlier. So the inspiration for this video are a couple of different collabs, different like online tutorials. There's one by Apoory Nandan, which is really helpful. There's another one showing the exact implementation of multi-head attention, which is very nice as well. And there's probably another 5 or 6 that I was reading into and I got a bunch of knowledge and inspiration from, but I don't actually know. So to those guys, I will do my best to dig those up and put those in the comments. If I don't, I am deathly sorry. Aside from that, the way that transformers work are actually, I think the best way for me to do this would just be to look up a transformer diagram AI, and then we could build out each module in a sequence. So the way that a transformer looks is basically like this. This is the, I believe, diagram straight from the paper. Attention is all you need. And what this looks like is this is an encoder decoder model. So this actually includes both the encoding half and the decoding half. It's important for me to note, and this is something that I only figured out relatively recently, the transformer in a generative sense, the one that, let's say underlies GPT, generative pre-trained transformer, does not include the left half of this diagram. So you don't actually have the encoding side of this at all. And what that means is you can actually remove the inputs here from the encoder side into kind of the middle of this decoder side. And to simplify it even further, you can actually just get rid of one of these 3 blocks entirely, like the second add and norm and multi-head attention block. So what you end up with is basically if we just remove output and put it back to input and remove the whole shifted right aspect, you end up with an input, which is essentially just a matrix containing a bunch of rows of your tokens, of your vectorized words. That goes through an input embedding. That embedding is a token embedding, which is then added onto with a positional encoding, which is just another embedding layer. And you'll see how we implement that in a second, which then goes into this model. And this model has masked multi-headed attention. You'll see the masked here is only present on the first kind of block. It's not present on any of the other blocks. And that's because when we train the model, we need to mask all of the inputs aside from the current word that we're on. Like you can think about it during training, if the transformer knew about the inputs to the model in the future, then it would simply learn and kind of memorize those inputs one by one. It wouldn't actually be able to develop that probabilistic model for assigning words and predicting them. So we need to mask the input. If you're not sure on that, I'll show you guys what I mean by that in a moment. It's actually quite simple. We push it through this multi-head attention model, and then we add and normalize it. And we also, I believe, dropout in one of the implementations that I found. So I'm going to be including dropout. And then after that, we take the output of this add and norm layer, we put it into a feed forward layer, push it through another add and norm, and then linear softmax, get our output probabilities, and then use that to assign the probability, or rather assign the next word, which we can sample using stuff like top K sampling. And there are really a bunch of methods. But anyway, if all of that sounded like French to you, or if you are French, if it sounded like German to you, I am going to walk you guys through what this looks like step by step. And hopefully by the end of this short video series, you guys will understand how to build one of these out in Python and in TensorFlow rather than like a PyTorch module or something like that. So let's get started. The first thing I'm going to do here is going to look like magic, but it's not magic. I simply know all of the imports that I need to do ahead of time. If you guys were making this project on your own, you guys would probably be importing modules kind of haphazardly as they come up. So I know that all of these modules are going to be required in some way, shape, or form, which is why I am importing these. If you guys are working on your own, as I mentioned, it's going to be a little bit different. So we're importing TensorFlow as TF. We're also going to go from TensorFlow import Keras. I don't actually know how to turn this thing off. That's really annoying. Yeah, I remember there was some like way to turn off the super cool turn off collab animation. What's that called? Okay, so we go to Tools, Preference, Miscellaneous, set power level to no power. So I need to uncheck corgi mode, I guess. So I'm gonna uncheck corgi mode. I'll go to no power. So there you go. That's probably a little better. Um, from TensorFlow.keras, we're going to import layers. And then from TensorFlow keras layers, we're going to import text vectorization. This is a module that's going to allow us to vectorize the text. So it's pretty cool. And I had a little spelling error there. After that, I'm also going to include this dash exclamation mark NVIDIA dash SMI. This is important just so that I can figure out what GPU I am using when I do this. And apparently I have too many open sessions, so I'm going to terminate one of them. It should be fine. And then I'm going to run this again. And when you do this, your runtime should be set to GPU for your hardware acceleration. And hopefully, fingers crossed, we can get a GPU of some kind. If we can't, it's okay. We're not going to need it for this video specifically. And unfortunately, we got a K80. I mean, it's not the worst, but it's also not the best. That's okay. Anyway, we're just going to include this as the top level kind of like import modules module. Next step is we are going to start off on the very first aspect of this GPT, or of, I guess, this transformer architecture. And that's that very beginning. This little input goes into this input embedding layer, and then that is passed through a positional encoding layer. And really, we're just going to combine these two so that the inputs that are vectorized just pass through one layer called the, let's do input and positional encoding layer before they get fed into our model. So we can do that pretty simply. How do you do this in Python? Let's do input position. Actually, let's do token position embedding. That's probably more realistic. So class token position embedding. We're going to define an init with the following parameters. We're going to need the max length of the sequences. We're going to need the vocabulary size, and I'll get into all these in a second. And we're also going to need the embedding dimensions. Now, I'm just really quickly going to write out what this looks like first, just in code, and then I'm going to explain it in a second. So this is just basic Python syntax, I believe, for just starting any class. You always just define underscore underscore init, and then you super whatever the class name is, and then you initialize to get whatever the parent properties are. That's pretty standard across a bunch of different languages. I'm going to define two layers here. The first is going to be token underscore embed. And that's going to simply be a embedding layer from the layers module that takes as input the vocabulary size and outputs the embedding dimension. Again, I'll talk about what this means in a second. We're also going to grab the position embed, and we're going to do both of these at the same time. So I'm going to create another embed with the maximum, or rather the input dimension to be the max length of the sequences, and the output dimension to equal the embed dimension. And because one of the most frustrating things for me anytime I'm watching a coding tutorial is people that screw up and don't notice their screw ups for a very long time, I'm just going to really quickly read this over. Yeah, that looks pretty good to me. And we're going to use a call method as well, and that call is going to be done on inputs, and I will talk about that in a second. Okay, so this first aspect here, this token and position embedding that we are kind of combining into two, both of these here are now just kind of slammed into one. These do a couple of things. The reason we're taking these parameters like max length, vocab size, and embedding dimension is because we're essentially transforming a vectorized sequence of words. So like a vectorized array, if you think about this being fed in one by one, or like a vector of just a sentence, which is just a series of like numbers that represent words. And then since there's a bunch of them, it's like a sequence, it's like an array. We're taking them from whatever that dimension is. We're cropping it at like 80. So we're saying that the max length is 80. And then we are transforming it using these layers, this input embedding layer and this positional encoding layer, into are embedding dimensions. And embedding dimension is a hyperparameter that we will pick that basically says, hey, how many dimensions do we want this transformer to represent these words as, right? Vocab size here is another hyperparameter, and you can choose literally whatever you want for this. These simply have like compute ramifications for you. You'll probably get better performance in the model if you go up a little bit in vocab size from what I'm going to show you guys. But yeah, you can literally choose any vocab size you want here. I'm going to choose like 10,000, maybe 20,000. And embedding dimension, I believe in the papers they picked 256, but I'm not 100% sure. So we're just going to go with 256 for now. But yeah, essentially what that means is if I go to another person's explanation of what the transformer looks like, this is JLMR, and he's absolutely phenomenal. He created this visual walkthrough of how transformer sequences work. You'll see that during the embedding process, you actually decrease the dimensionality considerably in order to make the computation of multi-headed attention mostly constant. So the dimensionality, I think, becomes 64, and the embedding encoder input output vectors are dimensionally 512. And that's why we do things. And I'll walk you guys through this stuff in a little more detail in a minute. But if you haven't already checked out JLMR's walkthrough of this, so I'm not butchering his name, it really is phenomenal. Okay, but anyway, so we have this token and position embedding kind of class now. What we're going to do is we're going to define a call method to that class that allows us to take an input x. And an input in this case is just a series of it's just a series of like vectorized sentences, and we are going to turn them into these embedding outputs. So the way that this looks is we're going to have our max length be the shape of whatever the input is minus 1. So that's because this minus 1 is going to be, if you think about the inputs coming in as like x, y, and z, it's like a three-dimensional tensor, let's say. The inputs are going to be, or rather the sequence length is going to be the last dimension there, just because of the way the tensors are represented. So the sequence length, or the max length here, is just going to be tf.shape of x minus 1. And then we're going to calculate the positional embedding in a very interesting way. Normally, I think the way that they did it in the paper, they just they use some like incredibly complicated sign function in order for you to like create an array of positions and then use those, you pass them through the embedding layer and then add them onto the outputs. In our case, we are literally just going to get a range, so an array that starts at 0 and then ends at the max length of whatever the sequence is. So it's going to be super simple. It's literally just going to be a giant array like this, except this is going to be a TF range, so it's going to be a tensor instead. So whether or not this is the best approach to positional embedding, I don't really know. I don't really think so. I mean, if it was these super fancy pants papers with these theoretical mathematicians, they probably would have used this. But whether or not it works really well, I guess, is up for debate. But it works well enough for our purposes. And you'll actually see later on when we train the model, it is actually capable of doing a pretty good job just based off this. Okay, so positions or TF range, start 0, limit max like that. That makes sense. We are then going to pass these positions through our position embed layer. And we are going to pass, positions. So positions equal TF range start 0, limit max length. This is what it was before. We're then redefining it as the result of this position underscore embed layer, which basically takes this max length sequence and then transforms it into this embedding dimension sequence. And that's going to be our new positions. And then we're just going to do the same thing with our x's. So we have the x's, and we're just going to pass these through the token embed layer, and then we're just going to return x plus positions. So at the end of it all, this is what our class does. When we initialize it, it creates a token embed layer, which is a layer that just transforms your input dimension of vocab size to an output dimension of embedding dimension. So if the input dimension is, let's say, 20,000, because that's our vocab size, this is going to transform it to output dimension of 256. And really, it's just a bunch of matrix multiplication at that point. I mean, really, that's all machine learning is. But the second layer, the positional embedding layer, is going to receive as input this max length here of, let's say, 80. and it's going to transform this shape of 80 to 256. And that's really what both of these, I guess, layers do. We're then defining a call method on that class that defines max length as whatever the shape of the input is, the last, I guess the last like subarray, the last position of that. Then positions are going to simply be a very simple array, a TF range, that literally looks like this. And then we pass that through the position embed. So now the positions don't look like 0, 1, 2, 3. Now there's not just 80 of them, there's like 256 of them. So it might be like 0 point whatever, these crazy numbers here that, have no real human representation, all the way up to embed dimension. And then we take the x's, we pass them through this token embed, and then we return x plus positions. If I put this here on the left, and then I put this here on the right, we'll see that we essentially are doing everything that this diagram in the paper is doing in one class. We get our inputs, which is our x's. We pass them through the input embedding, which is this layer right here. Then we add on the positional encoding. So we do the positional encoding, and then we add it on. And then that becomes the input to the model. So that's how that aspect, I guess, of the model works. And they're totally about to kick me off the GPU here. I forgot that Colab was like that. That's unfortunate. Okay, next up, we need to actually take these inputs and we need to define or pass them through a transformer block. Now I'm going to define the transformer block in a couple of different ways. I think right now I'm just going to use the built-in multi-head attention module that comes with Keras, and then later on we can actually create our own multi-head attention module that takes the same inputs in and that we just swap out kind of like a Lego block. But we're going to define a transformer block, and I'm also going to talk a little bit about that masking here earlier that I mentioned as well. This transformer block is going to take in as input self. It's going to take in the number of embedding dimensions. It's going to take in the number of heads. I'm just going to put an underscore there so everything looks really similar. And then we're also going to take in the learning rate. Let me do that here as well. And I'm just going to say 0.15 for that learning rate. Talk about this in a moment if you're not familiar with it. Inside of this, we are going to do the standard Python thing that I see all the time, which is just we're going to, I guess, inherit the properties through what's it called, the method resolution order, I believe. And then we're going to start defining and actually creating our model. So again, I'm going to put this on the left-hand side here, and I'm going to put the actual transformer diagram on the right-hand side, and we will see here that we have this. This is all taken care of. Now the inputs go into this multi-head attention module. And really what I'm doing, as I mentioned, is I'm using the model on the right, but I guess the model on the left is actually approximately the same size because we're supposed to remove one of these. We really want to simplify it down. This is essentially just going to be like a proof of concept, of theory, not necessarily performance. So yeah, it's just going to be two sections. It's going to be this multi-head attention, which is going to be masked, add a norm, and then feed forward, add a norm. That's literally what it's going to be. But anyway, so these inputs come in, and then they go through this mask multi-head attention model. So as I mentioned before, Keras is great because it actually has a multi-head attention model. All that multi-head attention takes in here is just the number of heads, which we already defined. And it also takes in a key dimension property. Key dimension is just another way of saying like embedding dimension. So you see those different words in the literature quite often. After that multi-head attention module, we see this add and norm layer. So in our case, the add and norm layer is going to include a dropout as well. So I'm going to have another layer. I'm going to call it just dropout one. I can get a little messy here. So we got to be, I guess we got to be cognizant of that. Dropout one is just going to be a dropout layer that takes in learning rate. Then we're going to normalize that output using layers, layer normalization. And epsilon, I think, is normally defined as 0.001. I believe that you get better results if you do 1e negative 6, not negative 5. Yeah. So we're just going to roll with that for now. After it's add and normalized, we actually take care of the adding a little bit later when we actually define the call method, so don't pay attention to the add part now. We will pass that through the feed forward layer. And the feed forward layer looks like this. It's just going to be, let's just do underscores. It's just going to be a sequential layer. And the sequential layer, oh boy, I am way too used to denote an automatic formatting for me to use this. The feed-forward network just looks like this. We create a dense layer. We'll pass in embedding dimensions. The activation of this first will be ReLU. And then we will add on another embedding dimension here. And I think we have two. We have embed dimensions, and then we have embed dimension. And I don't actually remember if that is purposeful. It may be not. But we're just going to roll with this for now. This embedding dimension is going to take, yeah, it's going to be the same here, an embed dimension with an S. Okay, great. After that, we're going to do dropout 2. That's just going to be layers.dropout because we're doing this again, right? We have this add norm layer, and that includes the dropout. We're going to take in learning rate. Then we're going to go norm2. That's layers.layer normalization. And again, we're going to define the epsilon as 1e -6, just like we did before. And then after that, that is pretty much our layer. We just passed through the input that we got previously. From here, mask, we're creating like the architecture of the model. This multi-head attention here is applied. Then we do our various permutations to this. So we drop out, then we layer normalize, and then we pass that through the feed forward network. Then it's a 2-layer feed forward network. The first layer has a ReLU activation. The second layer is just the embedding dimensions. Then we have a dropout again, and then we normalize the output of that, and then boom, that's basically it. After this, what we're going to do is we are going to define a call method on this, which takes as input an inputs. And here we're going to do some funky kind of math to figure out what the lengths of the various tensors are. So we're going to have a batch size variable, and we're also going to have a sequence length variable. They're going to take tf.shape of inputs 0 and tf.shape inputs 1. That's because the inputs that are being passed in are this, x plus positions, and the shape of this is going to be embedding dimension. We're going to pass in batch size. Batch size is going to be the first parameter, so you can imagine how this is basically going to be batch size. Sequence length is going to be the second parameter, so this is going to basically be like the sequence itself. And then inside of that sequence, we're going to have like a number of tokens, basically. So I believe that's going to be the embedding dimension here. And that's basically what that looks like. Okay, after we do that, what we're going to have to do is we're going to have to define what's called a causal attention mask. Causal attention mask is basically, if I just search up a causal attention mask, you need a way to hide, let's see if they have this. You need a way to hide, here you go. You need a way to hide the earlier inputs, and you need a way to hide the later inputs from the earlier inputs while you are calculating attention, because if you did not hide those later inputs from the earlier inputs, remember we're doing this in a vectorized way, so we're just a matrixized way. We're supplying the entire matrix at once with all of the rows and all of the columns. If you didn't do this, it wouldn't learn any interesting relationships between these words. It would simply memorize the training set. So it would say, hey, after the word hi is the word how. After the word how is the word are. After the word are is the word you, simply because that is what was supplied during training. We got to make it work a little bit. And in order to do it in a very optimized way, we use masking. Now, masking basically means when we supply the attention weights, which looks something like this, to the model, we're going to multiply it by a mask. You can also add it by a mask. But basically what that means is any area here that's in dark blue is, from my understanding, unaffected. Any area here that's with these white squares is either going to be multiplied by negative infinity, or it's just going to be taken out of the equation entirely. It's just going to be turned into zeros. This allows the attention weights to only depend on the attention values, scores that are found earlier, rather than the ones that are found later. And because now, let's say it's only this block that's ultimately responsible for its discernment of what the next block is, it allows it to learn very interesting relationships between words and sequences and positions and so on and so forth. So that's the idea behind a causal attention mask. We don't actually have a causal attention mask yet, so I'm actually going to define it up here because we're going to need it. So let me see. Let's just call it causal mask. causal mask. Let's go batch. We'll also do size. And all a causal mask is going to end up being like is a giant matrix like this. It's going to be like 1, 0, 0, 0, 1, 1, 0, 0. You can imagine how if this was like a one with 4 inputs, 1, 1, 1, 0, and 1, 1, 1, 1. This is literally what we're creating here, so it's nothing fancy, it's just a little bit of programming. All right, so x in this case with tf.expand dimensions, tf.range size, and 1. If we were to go tf range size would be, oops, I forgot a bracket there. If we were to do tf range size would basically just mean I'm doing like an array of like, this all the way up to whatever size is. So if I'm expanding the dimensions of that, what I'm basically doing is I'm just adding an extra dimension and I'm making it so that it's like this. 0, 1, 2, 3, 4, 5, and all the way up to, size. The reason we're doing this is because we're going to multiply these out later, the range and the size, in order to produce a quick little matrix. So after that, we're going to create a mask. Mask is just going to say, hey, is x greater than y? Actually, let's do greater or equal than y. And then we're going to simply do this. Reshape mask so that it is now 1 size and size. So now it should be 3-dimensional. And then we're going to tile it. If you guys know what tiling is, just multiplying the tensor by the various shape dimensions. And then we're going to return the mask. So I believe that's pretty much it. If I were to, let me just define this up here actually. And then let me run causal mask batch, let's say 1 size 5. Let's just see what happens. I may have to print this unless I'm not connected to a batch. Oh, sorry, I added another dimension there. Yeah, okay, cool. So we have a shape 1, 5, 5. We have an array with 1, 1, and 5. And if I were to change the batch dimension to, let's say, I don't know, let's pretend our batch is 3. It's really going to probably be 64, but let's roll with 3. Yeah, now we have 3 arrays and they're 5 by 5. Okay, great. So you can see here that the causal mask is set up so that it's a true and false matrix. True is basically just going to leave whatever the value is alone, and then false is just going to eliminate that value from future attention calculations entirely, and that's how we're going to do it. And every row, it's going to be another kind of training example. We can compare one row with the other in order to determine kind of like the training and the targets, and it's super useful in that way. But just for clarity's sake, I'm going to remove this model, add it here, and I believe it's CMD. Yeah, there you go. And then I'm going to continue on with this model here. So now that we've defined this call method, we are going to add our mask in. The mask is going to be our causal mask, and we're going to provide it as input the batch size. That's why we found the batch size back here. And we're also going to add in the sequence length. Sequence length, so basically the number of words in a sequence. Again, the reason why is because that'll dictate the size of the matrix. Remember, we have sequence length and size. Size means it's going to be, let's say sequence length is 10. It's going to be 10 true-false values across and 10 true-false values kind of vertically as well. Now we're going to define the Mha calculations. That stands for multi-head attention. So actually, let me just make it even simpler. Multi-headed, and in this case, it's going to be self-attention because that's what the paper says. So we're going to go Mha out, and we are going to use the attention layer we defined up here. We're going to pass in inputs, and then we're going to perform self-attention by supplying inputs as the second parameter. And then the mask that we're going to provide is going to be the mask that we just made up here. This is because attention mask is an optional parameter supplied to the multi-head attention module for Keras. And we created our own because I believe the rationale was you just get better performance on small models of true-false, but I may be mistaken. We're also doing dropout 1 underscore out. And we're going to pass in the output of Mha into this dropout layer here. Then we're doing norm 1. out. We're going to do our norm1 layer, and we're going to do on the output of the dropout1 output. And then we're also going to combine that. So let's do combined 1 out, and we're going to add norm1 out plus the inputs that we provided at the very beginning of the model. The reason for that, if I still have that calculation, is because if we go back here, we see that the output of this add and norm layer is actually, the reason it's called an add and norm layer is because the input to the MHA is actually, I guess, sidelined here and added into this normalization layer, which we also included dropout. And there's a specific term for this in machine learning, but I'm not a machine learning expert, and so I don't actually know. Cool, so that's our combined 1 out. We're then going to do our feed forward module. And what that's going to look like is we're going to have an FFN out, and that's just going to be the feed forward network that we've already defined, and we're going to pass through combined 1 out into that feed forward network. We're also then going to do a dropout 2 on that again, because like I said, we're just applying the exact same dropout layer normalization method again to the outputs of the feed forward layer. It's the exact same thing. Then we're going to get the output of that, pass that into our norm 2, which is dropout 2 out. I wonder if I could just combine these two. No, I couldn't combine them. And then, oops, I'm going combine 2 out, and that's going to equal the output of norm 2 out. And we're going to add on the output of combined 1 out. And that's because we have this kind of connection here as well. We have the, I believe it's called residual connections, now I'm thinking about it, between the output of add and norm and the input of this add and norm as well. So we're going to add these two together, and then whatever combined 2 out is, we're just going to return it. And that basically takes us to here. And this linear softmax stuff we can deal with at another time. All right, I believe that is it for the transformer side of things. And I think at this point we have essentially fully defined a transformer in Keras, in TensorFlow, with these two classes. We have the token position embedding up here. We have the transformer block down here. And I could even add this causal mask, which is part like another class here. So let me do that as well. It'll take in self, batch, and size, and then we'll just do self dot causal mask, batch, size, sequence length. Yeah. That way everything is just combined in one. I'm not very good at object-oriented programming, as I'm sure you guys can tell. So, you know, I'm kind of picking this up as I go along, but at this point now, everything is combined in that one transformer block class and that one token position embedding class. What we have to do now, and what I'm going to leave for the next few videos, is we have to take the output of this whole shkaboom, or actually this whole shkaboom, pass it through this whole shkaboom, and then we actually have to like define all of these variables that we've created here. So max length, vocab size, embedding dimensions. We have to define these hyperparameters, load in a data set, and then actually create a function that allows us to sample from that data set efficiently during training. So without further ado, that was that. I hope you guys enjoyed the first preliminary video on how to implement transformers completely in TensorFlow. I'm still kind of learning myself a lot of these things, so if you guys have any better ways that you've personally found to implement these various functions, if you have better explanations that you guys could use for, let's say, like tensor shapes, it's something that I personally really struggle with, I would love to hear it. Please leave your comments down below. In the next video, I'm going to be implementing what I talked about, which is the hyperparameters, as well as, you know, how to create a function that allows you to sample from this during training. And then the last video, we're actually going to do a little bit of training. I hope that was useful, and I will see you guys in the next video. Thanks.